If the velocity is constant, this charge particle never radiate.
It does, yes, yes.
Yeah, you have to modify its velocity, which means that we have to accelerate this particle. But here, the acceleration is given by the change of the trajectory.
Yes.
In fact, it is always
Yeah,
already
it's changing.
yeah. And when you change the trajectory,
Yeah.
you accelerate the particle. And because the particle cannot go beyond the velocity of the light,
Right, yes.
then it is slowed in its own field, in fact. And then it has to produce,
This is the light.
yeah. And because it releases the light, the electrons will lose this energy and they cannot stay in the same orbit. And each turn, somewhere in the machine, we have to give back the energy lost. Yes, every turn. Yeah, and this is given by what we call radio frequency signal, which the particle should come at the right moment to get this energy, and then the particle will stay forever. Yeah. Yeah.
And the magnets are on the sides.
Yes, exactly. So you have different types of magnets. What you can keep in red are we call bending magnets. You need magnets just to deviate
The light.
the electron. The electrons. But when you start to have billions of electrons in a theoretical orbit,
Yes.
but in their travel, they can be modified. So you don't want them to modify the trajectory. So you have to focus them around the theoretical. Then you put like lenses. Here, these are magnets called quadrics. When the particle is going outside the theoretical orbit, up. Yeah.
But see, as it gets close to the speed of light, yeah, it that changes to because we have the wave particle to other nature. We have particle changes to the wave.
Yes, the electrons will produce light. In the light, you have different waves, like wavelengths.
Okay.
Yeah. And so this is really one of the main characteristics of the synchrotron light.
Yes.
It's let's say you can say that it's a very large spectrum.
Yes.
Red point, you can have the light, and this light can come from infrared to hard X-ray.
Yeah.
And you have to put in your beamline what we call monochromator to select the energy you want. Okay, then you do your experiment. Okay, and it's as John mentioned, we can look at in such a synchrotron machine. In fact, you can have up to is actually 30 simultaneous experiments, in fact. Because and this is really fantastic because otherwise we have to multiply the number of that's good. I hope one day we can have a simple one next to it.
Okay, so we see what we do for one, okay, and then we go to the so this is oh, okay, so this is
You know, it's not just anything. One difference, but here we it's using.
no, no, no.
That's more critical.
Yeah, right. What we need is an ecosystem. To get the most Hello, no, we're here.
We go downstairs and then.
And this is where that. And
It's a medium circumference. Some circumference twice larger than this one.
okay.
Yeah. The classical is, this is the big line.
No,
Go down.
I did.
Hello,
Hello, hello.
Hi.
Thank you, thank you,
Yeah,
thank
you're
you.
welcome.
In Beamline, not actually right. Okay, welcome. Your Beamline dedicated to ultraviolet. So actually, there is 29 beamlines. Most of them are working with X-ray. A lot of different things from hard X-ray, soft X-ray. But this is a particularity of Soleil. We also have infrared beamlines. We even have two infrared beamlines, which are the infrared village, and also ultraviolet beamlines. We are three beamlines here. In fact, Disco, Desir, and Pleiad are three beamlines dedicated to ultraviolet. And this is this low energy beamlines. They are quite popular because these are easy experiments to run because we are not under ultra vacuum. This is easy to bring your sample, to put it on a microscope, or Frank will show you the beamline scientist with me, to look at your proteins and everything. So these are easy beamlines where we welcome quite a lot of users from France, Europe, but the world as well. It's quite a popular beamline and very easy to look at samples because we don't need to go to ultraviolet. So we have two branches on this beamline. We call Disco because the D is for dicrease. UV dicrease to look at the protein folding and unfolding, but Frank will show a bit the setup and what he does with this. And we also have another setup called for imaging, which is also very versatile. When we look at very different range of samples, I took some images. This is all the image we can get from deep UV. So deep UV is very nice because it makes samples fluorescing naturally. You don't need to add any marker. So if you look at this, are stems of flax. So this is a student working on this. This is a postdoc student working on flax because, as you know, flax is maybe the first fibers that have been used for tissues. And in Egypt, we went with Alicia to Egypt to visit and to look how fibers were prepared, and flax fibers were prepared in the Egyptian time. And France is also very good world producer of flax. In the north of France, in Normandy, we produce a lot of flax because
has to be a lot of water there, and it works very well. So France invests in how to use flax today. We make new materials, composite materials, and the project of Alessia is to do smart textiles. We want to design new textiles that will adapt to the temperature, to the humidity, to your health. So they will add fibers, and to these fibers they will have small detectors, molecular detectors, that will be adapted to do this. So this is a big project, a European project for upwards. There's many people, but we do a lot of different things. I can show you. We do also a lot of tissues with deep UV. So this is a big project we had with a physician, a pneumologist, working on lung tissue, and this was after the COVID pandemic. We studied this because when people were under SARS-CoV-2 contamination, they had this oxygenation, sur-oxygenation to help them breathing, and this affect quite a lot the tissue, the lung tissue. So we have a project to understand the effect of this over oxygenation on tissue, and here, without any labeling, so that means we don't put any colors, we can detect proteins and how these proteins are affected into the lung tissues, and in particular this was collagen and elastin. They were quite different. So this is a lot of different things. We work with cells as well. I put some video. Here is quite particular behind this beamline, because we work with living samples. We can work with living cells, living bacteria. We work with enzymes to digest lung tissue, because deep UV is very good for this. It's not sensitive to water, so we can work with living samples. So this works a lot. And we also have the chance to attract a lot of people from the museum here and ancient materials, because with deep UV light, synchrotron deep UV lights, you can probe pixels from this painting. So we have a lot of people coming from museum to look at how they. One example is, for example, this Picasso painting of it's called the woman. I don't know if you see the arm. It's a bit yellow and it's getting a bit brown. So the color of the painting is changing. And the researcher come here to try to understand why inside these pigments, why affect the color and why the color is changing. And deep UV, of course, they don't want to modify the painting. Deep UV lights allow to follow this, the constitution of these pigments and why they change over time. This is something we can do. So a lot of biology, a bit of materials, and we also have other projects that Paul Dumas is working with us here. A project on high pressure using deep UV. So I don't know, Paul, if you want to explain your project.
And trying to invite a biologist. At the beginning, but now yes, they accommodate. In fact, the problem is comes to materials. All today, materials are used in extreme conditions, reactors, for example. So what happens with this? You typically the surface of the can of the can is metallic, and metallic is a alloy of metallic. So you want to know how this behave when temperature increase and the pressure increase, especially in reactors. So the way to study is to behave, how they behave with the reflectivity and the conductivity and so on, is to look at the reflectivity in the UV, because that reflectivity is directly related to the physical aspect, reflective index, electroconductivity. You can rely all these parameters together. But the problem today is on the people working on this typical behavior, they do calculation. They just simulate how this can behave and change as for sharp pressure. But in fact, as you know, if you do a DFT calculation, you bring some parameters and hypotheses. So they want to check. They really have a needs to have at least reference point that they can realize and compare with the theory and see whether the approximation they are using are appropriate or not. So this is the goal here. So what we do we have the high pressure cell. In fact, we have diamondville cell coming at pressure to very high, and we look how they behave in reflectivity with the UV. So, following this, we know exactly, we can calculate exactly the reflectivity change of the materials on many of them, gold, copper, alloy, and so on and so forth. So for doing this, we needed a special equipment that they didn't have here. And we know also that they are using a lot of biology. They are very successful scientific activity here with the biologists. So we just wanted to get there, plug it in, and remove without disturbing these people because they are doing very nice things. So of course, he pay me for doing it. We have a chamber which is at the end there, and it rolls and just capture the UV and return the light just on the purpose. That's all. It takes alpha day to set up and alpha day to remove. And then we really have already good papers, good publication on that.
In fact, I make a selection of what I speak about, so I can give you these papers. This is a paper of Paul as Nature Communication recently. It's only from this year. This is something I speak about living cells and bacteria. We work a lot on antibiotic resistance here because this is really what the was the World Health Organization recommend to spend a lot of research in this antibacterial resistance. So we work a lot on this. About the Egyptian things, I took this one, Alicia. This is how about the fibers that's been studying here to understand the way past from the past, so how the fiber changed from the Egyptian times to now. And then I also took some amyloid and DNA work that's strongly. So I can give you some of this if you want to have some reference publication. You will find them. But now I can show you the instruments if you want. Because, we do a lot of research, but we like also develop instruments on our beamlines.
So the lung tissue, take the full lung. What? So for the lung tissue, say take small samples of the lung.
Yeah, we do
That-
biopsies.
Okay,
This
all right.
physician that we product biopsy from the patients,
Okay.
and then he come here
Uh-huh.
and he works during the weekends. He's a very hard worker because he works at the hospital,
Uh-huh.
try to care people. On the weekend, he comes here to do the study these samples. It's Professor Sambaya.
Okay.
And he wanted to understand the effect of this over oxygenation.
Okay.
So this is the instrument we're using. So the synchrotron is off now. I guess Amor explain you that we're doing an upgrade and they stop the machine. So the synchrotron arrived from this tube here. The bending magnet here, the source is a bending magnet. So it's quite we don't need a non-relator, we don't need a big extraction, just a big dipole magnet. And then you can collect deep UV lights from this. It's about 40 meters far from here. It's quite far. This is a big advantage of synchrotron. This radiation light is very focused, so you can really go far. And then we arrive to a small monochromator here. And this is the microscope. They look like microscope, but we modify them because the big problem of UV, deep UV, cannot get through glass. The glass stops the UV. So if you take normal objective or normal microscope, it will not get through. So what we do, we have to develop our optics and we have to develop our own microscope to do these experiments. But then once you've done this, everything will fluoresce and you will have nice images without any labeling. So here we do this to do this live imaging for live samples like this. These are cells that are infected by viruses. So this is a visible light. So we can put living cells on the microscope, and then we follow by time. How you see when the virus attacks the cells, they tend to get explode That's what we see here. And we can follow without any labeling, any markers. We can follow the impact of the cells of the viruses of this cell. Was a Nile virus. So was very spread over walls, the Nile virus. So this was a study here. So it was not exactly the virus because here we are not in the biosafety strict prediction, but the virus has been modified just not to be contaminated. But we managed to do it here. So that's what we do. And here we record spectra because this is to do a setup dedicated for recording a deep UV image. And here we can record, instead of recording an image, record a spectra. And this is very interesting when you have two a spectra, something that's changing a bit. We can follow it by the spectra signature. So this works very well here. Now maybe we can go to visit Frank's station.
Okay.
So Frank, here is we study cells and tissues. And Frank go much lower than here. He study molecules and complexes.
Much lower.
Here I effectively do more molecular biophysics, if you like. It's the circular dichroism. We take the property of the UV light being circular polarized. So, linear polarization from the sunglasses, these ones, they protect your eyes and they diminish the reflections. But we can produce circular polarized light by modulation, phase modulation, or water wavelength shift, and so forth. And then the big advantage here is that the synchrotron, as opposed to in-house machines, we can go down in if we're working with samples in water, which most biological samples are suspended in water or in the water surrounding. We can go down here to 170 is the limit. 168 is really the limit for absorption of water. And if we work in film, we could work down all the wavelengths down to 120 nanometers. So you imagine maybe crops and seeds that are dried out and there's still protein in. We would like to understand the folding of those in the very low range. So if we excite with UV in the circular polarized light, what happens is basically the absorption originates in the peptide bond. That's the N to pi to pi star transitions that we're looking at. And so these have been known. I mean, it's very old. Moffat in the 50s in the States, he discovered basically the origin of the absorption. So it's due to him, and that he attributed the absorption edges of the orbitals, and basically that understood. And so traditionally, the secondary structures. So if you take a protein, fold it in an alpha helix form, then you get very characteristic alpha helical spectra, which comes from alpha helical protein, with very fixed positions here, 222, 208, and here 191. So basically, you could say that an in-house machine, you could gain access to all this, but there's a problem because there's sort of it's called a bathochromic effect. That when you're close to the absorption edge, then you shift the CD signal. And so we need to go down to 120 and fall in the lower wavelength range. So in this range here, below the N to pi pi star transition being perpendicular, we observe the charge transfer. So I've been recently in a congress in Japan, and they're very interested. It was a meeting on quantum spectroscopy. And I'm not really doing quantum spectroscopy. I'm a biologist, not a physicist, maybe biophysics. But the charge transfer is a region that you can observe with quantum mechanics and you can describe. And basically in this area, so you must imagine from one peptide bond, there's an electron jumping to an adjacent peptide bond. And so it's like a current going off.
So the other focus, so I've been doing my studies, my PhD and my postdoc in King's College in London. And basically then I went to Birkbeck. I'm a crystallographer from my PhD. And basically the SRCD was a new tool which we developed over the time. My postdoc, I had two students doing their PhD, and Bonnie Wallace was my boss. And we explored synchrotrons in the world. So we went to Brookhaven. They had at the time, they had a dedicated UV beamline and infrared beamline, just dedicated synchrotron basically for it. And Aarhus in Denmark, and then there's one in Japan, in Hiroshima, another one in Beijing, and now they built one in Brazil. It's more or less not working. And then there's still one in UK. So these are the distribution of circular dichroism stations in the world. And basically, during my postdoc, I've been working on the standardization and normalization of these protein spectra, because you take a spectra based on these three characteristic spectra: alpha helix, beta sheet, and random coil. You could basically deconvolute any spectra and say this is the amount of folded protein, alpha helix, beta sheet, and random coil. But it's a more subtle. And so over time, we know that there were like 5 algorithms to resolve the problem and to get more detailed information. And basically, when I came here, there were big errors, and you had to use one algorithm for the alpha helices, one for the beta sheets, and we were not in artificial intelligence; it was own intelligence to understand what's going on. And basically, I collaborated with a group in Budapest, Joseph Carlos and Andras Mixonai.
Okay.
And with them, we went through the reference data set that I collected during my time in UK. And we discovered actually that there's a link, that there's a correlation between the twisting of the beta sheets. So we could identify that beta sheets being not planar, flat, most likely twisted left or right. And depending whether it's a parallel or an anti-parallel beta sheet, you get different signatures and spectral absorption. So they correlated in the PDB all these beta sheets and the spectra that we had already from known structures. And we deconvoluted it, we reorganized the new algorithm, best cell, which is the third most cited paper in at Soleil at the moment. So 4,000 citations. And we keep on working with them. They come every year and we upgrade. And now it's been included in the top bench machine, the JASCO. So we get a lot of citations.
Okay.
Perfect.
Yeah.
It's not for the money.
Yeah.
We don't get any money from the Japanese. We get the fame. And so this was a very nice success story. And nowadays, so this has been going on since 2015. We started to publish. And so this has been going on. And now we have the other major class of biological samples, which are the nucleic acids. Then came the COVID, and we published books, methodology books here. This was the first one here. This came out right at the COVID time in 2020. And recently we republished a new one. So here we have methodological approaches, descriptions of protocols and stuff like that. And so at that time, we started doing protein and nucleic acid interactions. But for nucleic acids, it's far more complicated. Nucleic acids, they can be a double helix. And so you spread the electrons over 20 angstroms, as opposed to a small 2.5 angstrom long peptide bond. So the electronic transitions that you can observe are much larger and more varied. And as you can see, sorry, switching from one screen to another. As you can see here, we have many more oscillations going on, as opposed and a more restricted range for the proteins and larger band, spectral band for nucleic acids. And so I said, well, let's get a PhD student, and he will work hard, collect on purified and classified standardized nucleic acids. And let's get a company on board, Sanofi, because it's French, who were very eager to produce an RNA vaccine, which was not their field, right? They were doing classical virus particle vaccines and so forth. And now they wanted to go into this messenger RNA stuff. And so we were very lucky. They sponsored the thesis. And Kevin was working hard to get, we are now at 160 spectra, classified, normalized. And we also have the thermal denaturation of those. And now we have managed to organize again a new algorithm, not with those ones from Hungary, but internally. We developed a new algorithm to identify the folding of nucleic acids. And that's quite nice. I'll show you here. So we have now about 16 as opposed to 8 eigenspectra, if you understand. The eigenspectra here at the time in the 50s, 60s, there were 3. With them, we managed to obtain 8. And for nucleic acids, there are 18, as we say. And so we have now, a bit more statistics about it. But now we can deconvolute basically nucleic acids. And the next step will be to do nucleic acids and protein. Besides that, we have another setup. It's called the OCD, SR-OCD, where we rotate a sample. And then by rotating, we eliminate the linear contribution. So if you have a membrane deposited on the surface, and you get a protein, so you have an alignment, an orientation occurring. And this will absorb in the linear dichroism. But the photodetector can't distinguish between circular and linear absorption. So we'll only count photons, and then you have to do a mathematical analysis. Or you eliminate the contribution of the linear dichroism by making the sample holder turn over 360 degrees, and you acquire the data over 360 degrees. You eliminate linear contribution.
They are going to visit another.
So membrane proteins, amyloid research, a lot of amyloids here, because amyloids don't crystallize, you don't always get the right structure of it. So there's a lot of prion-like stories and things like that. And it's very good for students. It's very simple. I just finished.
Dementia.
You basically load the sample in the sample holder here, as shown in the video as well. And we have very small cells dedicated to the PD. And this is very nice because they consume nucleic acids are very expensive in synthesis.
Okay.
And so messenger RNAs, if you want to synthesize a messenger RNA, it's a fortune. and so we have samples of 20 microliters, which cost like 4,000 euros, right? And so you're asking what is the quantity? And the quantity, I'll show you this so you remember. What's the 2p? Okay, the 2p. We ceased operations. So yeah, 4 microliter. I can go down to 2 microliters. And that's the thing to recall, because we consume very little sample, precious sample. And even if it's toxic and so forth, it's contained in the cell. So we could do, so I put a 2 microliter drop on it. And now I take the sample. I didn't check whether it's clean now and so forth. But you see here the drop? Can you see it? Yeah. And now this is a 3 micron path length. So I need to have nucleic acids of about 10 mg per mil, something like that. And then I press, the drop is spread out. The rim is hermetically closed. I can do my thermal scans. This was very interesting for the idea of checking the thermal stability in the context of lipidic membranes surrounding the DNA, like in the vaccine, and to see the thermal stability of those. The whole idea was, I never understood why we needed to freeze at -80 these vaccines. Right? And so basically, if you have a molecular biology lab, you could do it in the lab.
Okay.
Without freezing. Sure.
Thank you. Thank you very much.
I'll jump.
Yeah.
Thank you, thank you, thank you.
Euh, il faut que tu sortes et tu rentres, hein, parce que tu peux pas passer sous cubain.
D'accord, bon.
Donc, tu prends la porte. Là,
Oui, oui, oui.
là.
D'accord, d'accord, d'accord. Oui. Just go out and then come back because you otherwise you have to go under this.
Huh?
But I don't think that's how it works.
That's toxic.
It's tough. You know, it's not that. It's not part of operations. Some guy don't need to. You go and
That's toxic. Hello.
Hello.
Bonjour. So, yeah, all it's a smaller group. this
Yeah.
one.
Yeah.
No one was lost during the. Well, since it's circular, I just have to walk somehow to find the starting point. Okay. So I'm Pierre Ferté. I'm the scientist in charge of the crystal beamline. And crystal is not an acronym. So if you have crystalline matter, so that's basically what we are studying on this beamline using X-ray. So we are at the other extreme, I would say, of the energy range of Soleil. You went to disco.
Disco.
Yes.
So it was almost, let's say, on the UV or low energy side, and here you're at almost the other extreme. So we use X-ray diffraction. So crystal is a diffraction beamline. I don't know if you are familiar with this concept, but so we can bring answers to the user that have structural issues. So with different kinds of materials. As soon as you want to link the properties of one materials or to understand the properties of any materials, in fact, somehow you have to understand its structure. And this means also understand this structure at different scales, going from the smallest one, let's say atomic scale, to maybe millimetric scales. So you have to be able to use different techniques to probe these structural properties at these different scales to understand the properties of your material. So that's why crystal is really concern a lot of different communities, going from, of course, physicists, chemists, but also material science, even biologists, mineralogists, earth science, ancient materials. So it's really a wide landscape of communities that come to use the instruments I will show you to study the structural properties of matter. So what does this mean? First, you have, so since the matter is built with atoms, you have to understand how the material is built at the atomic scale. So we can offer diffraction techniques to do that. But you can easily, let's say, do that if the matter is crystalline. If it's amorphous, you can have some information, but it's more difficult to have this. And what you have to know also, and you probably know that we offer techniques that you can find at laboratories. So it's not necessary to come here to make some of the experiments we propose here. So why do the users come here? Because they have already tried at labs what they can do, but it's not enough. So they need sometimes more photons or more flux in the beam, or they need smaller beam because they want to study small materials. And this is one of the reasons they want to come here. They also want maybe to adjust the energy of the incident beam to probe specific properties of the material, and I will give you an example. So this is kind of things you can't do at labs. So this is the reason why one of the reasons why they can come here. So let's start with some example. Yeah.
Could it be used then to characterize like lithium bomb to identify the rare earth elements?
Yes, it's not a spectroscopic beamline. So if it's, let's say, a kind of elemental analysis you can do, you want to do, it's not necessarily the right place to come because most of the time we are working at a constant energy. So we're just doing diffraction. But I can also explain with an example because we had some times ago, I had a PhD student that worked on photovoltaic materials made with copper and zinc. And copper and zinc in the Mendeleev table have just 1 electron difference. So and the problem was that this material crystallizes in a certain way. And there was a question about whether or not there was an order between the copper and the zinc in a certain plane of the material of the cell of the crystalline cell. So how the zinc and copper was ordered, and this was directly linked to the photovoltaic properties or absorption of light of the material. So understand if it was ordered or disordered was a critical issue, I would say. But you can't do that at lab because you cannot distinguish copper from zinc because they are too close electronically speaking. So they come here and we adjust the energy so that we were just below the copper absorption edge. So artificially, I would say, you will increase the electronic difference between copper and zinc. So that way you can have a contrast between copper and zinc. And using this beam, they were able to see that, in fact, the materials were in a specific crystallographic plane, the materials was disordered. So this then afterwards make some calculation to link with the absorption of light properties of this material. So this is one kind of answer we can bring because we are able to distinguish elements that sometimes is not possible at labs. Another common use also of the beamline to determine the structure of materials, of molecular materials, for example, is that either the single crystal is not that big, so you need flux to be able to measure, to determine the structure, or it has a short lifetime. So once again, you have to go fast to be able to find the structure of the material. So since we have more flex, let's say, it's easier for us to go faster than you can do at lab. So you can reach the structure of the material that you can't at lab. So this is one also another result. I propose to go inside the hut because I know that you don't have so many times. So let's go in and I will show you the experience.
How these differential options made. And so we about that. You really keep it up. Was not that and go.
Okay.
You get the point?
Yeah.
One of advanced analysis, I almost agreed. I know materials are not like the break. We are not support. Depending what you want to finish.
Yeah.
Very fun with you. That's why we had the initial fundamental argument, my argument always. You put it. At the end of incidents, I use some note out of some. I say they are good. Well, we don't know, we basically, but they are sorry, I guess. I don't know, I never was, we're gonna put it that. We are not shooting it down.
Are you coming from Zimbabwe or working in UNESCO?
No. He works for UNESCO Zimbabwe, but we came for Viva.
Ah,
Viva Tech. So all the 29 are with there.
yes,
29.
yes.
Okay, so different.
Yes.
Okay, all right.
You have circle
Uh,
and you have tangents,
okay,
and each tangent is one beam line. So at
Okay.
the end, you can count 29.
okay, all right.
Which means that 29 different experiments
Okay,
simultaneously.
yeah. So ideally, how many? If you had a big thing, how many would you have
It
to
dep-
cover all the domains of?
I think it depends on the community you have, etc.
Uh,
And today, 29 beam lines at Soleil are enough for the community we have in France or in Europe, etc.
Okay.
Because if you construct 60 beam lines, at the end, I don't know if you will be able to have 60 very interesting experiments at the same time.
Okay.
So you have really to balance with
Okay.
the budget and etc.
Okay.
And you have to also to take into account that each experiment, each successful experiment, is also a new paper to write.
Ah.
Are coming from the world. They evaluate the proposal,
Mhm.
and if the evaluation is positive in terms of a new science, or new idea to do, or new new way to think about new material or etc.,
Mm.
then they accept we receive every year about 1,200 proposals,
Mhm.
and we accept only half. Oh, yeah. 600 of them are rejected because the committees decide that they are not,
Okay.
yeah.
Yeah.
It's very
Something.
Alors, nous, on a, oh, yeah, he's got